afternoon. How are you guys? All right. So, just yesterday, I was talking with my wife about teaching with these HEPA filters and stuff, and she knows my nature is kind of soft-spoken. I don't normally project, and then got really worried all of a sudden when I told her, "Yeah, these filters are really loud, so I'm always like trying to project pretty well." She's like, "Uh-oh, do all your students think you're mad at them?" She says I have an angry voice when I try to project. So, do you guys think I'm angry at you all the time? Well, if you knew me with just the non-projecting, maybe it would feel like that. I don't know. So glad to hear that, because I'm not angry at you yet. Kidding. And I don't intend to yell at you by any means or anything like that. So I have my sound system working back how I normally have it, just through my laptop. I need to go check on the audio quality later to see if that's actually people can hear it. I do plan to improve that at some point, just in case you are watching remotely at some point. But thank you all for being here. I think it'll be a better experience from here because you can ask me questions. The audio is probably better. We'll see. And at any rate, I do kind of expect you to be here participating and using the online option if it's really something you just can't avoid. Can't avoid it. Another couple things I wanted to say. I have not yet posted the past notes or the past lecture, any of that. I'm a little behind on things as we start the semester. For me, this is kind of the first week because I was out at a conference and then IDA, all that. So bear with me. I think tomorrow I should have today's lecture and Tuesday's lecture posted, and I'll normally have those probably within the day, if not maybe the next day. So appreciate your patience there. At this point, you probably don't care too much because you don't have an exam or a homework coming right up yet. But on that note, I will probably also need to revise the syllabus in terms of the schedule we've got laid out. Might have to change exam dates. I'm just going to take a look. In terms of the makeup days, my aim is to take kind of the seminar lectures that I was planning. I think I was going to go through the Flint water crisis with you guys at some point and extract that from the normal routine and then just post it as a kind of a separate thing, maybe live stream it when I record it, possibly on the weekend or just whenever, and then tell you, hey, for this date's makeup class, watch this, and we'll have an activity about it, something like that. So that's kind of my plan at the moment. I do have to go through and kind of sort things out, but I have not done so yet. So I just want to let you know that's coming, but not here yet. Any questions or concerns for that stuff? Okay. All right. And I have not thought yet about our first homework. So we'll get there at some point next week. All right. So today I wanted to pick up partly where we left off last time. We were kind of covering the fundamentals of mass transfer, mass balance, what that means. We took a glance at this problem. I was hoping to project it, and then I decided not to last time. So I've got it up here for us this time. So what I would like you to do is read through this on your own or in groups, pairs, whatever, kind of just sort through it, apply your mental processes based on kind of just the word problem and perhaps what we talked about last time to start getting a feel for how you might approach this, and then we'll walk through it together in a couple minutes. So the problem is Mr. and Mrs. Consumer have no children. In an average week, they produce and bring into the house approximately 50 kilograms of consumer goods, food, magazine, newspapers, etc. Of this amount, 50% is consumed as food. Half of the food is used for biological maintenance and ultimately released as carbon dioxide. So that kind of disappears, right? The mass is still there, but we're not like thinking of it as stuff that's weighing inside the house. The remainder is discharged to the sewer system, and I think they're also kind of assuming that's ignored. That's that food to people section there. Then they recycle 25% of the solid waste that is generated in terms of like garbage. So 25% of the solid waste that they would normally take to the curb is recycled. approximately 1 kilogram, accumulates in the house. And then it says, estimate the amount of solid waste they place at the curb each week. Okay. And then the first bit of the solution is here. It says, begin by drawing mass balance diagram, labeling the known and unknown inputs and outputs. And they mentioned that you could do 2 diagrams, one for the people inside, like food coming into them and stuff, but that one's not really relevant, because if you did that, and I'll regale you with my glorious stick figures, if you did a mass balance into the person, you'll notice that that whole system is inside the control volume, right? So we don't actually need to worry about it, because whatever's happening in that smaller control volume happens within the bigger system, and so it's no change in the bigger system. There's no inputs or outputs across the other barrier because of the people. All right, so take a few minutes to work on that. I guess another way you could look at it is the people are out here. And so it's just sending food to people, and then you don't care what happens after that. Okay, so hopefully you've had a chance to at least kind of take a look at what are the inputs, outputs, and kind of features like that. And so we'll take a look through their solution in a moment and make sure we're tracking with them. But my first impressions are that we've got the input, it's just a total of 50 kilograms per week coming in. And then we were told that half that's food, that goes to people. And then from there it goes out as CO2 or out as sewage. And so I think that food to people here, if I'm not mistaken, that's just simply 25 kilograms per week as an output from the house. You bring in the groceries, you put them in the fridge, and then they go back out through consumption, right? And then, of course, whatever packaging that goes to the solid waste for recycle or trash. Then, in terms of, there's no other inputs, so we can split that 50 into 25 for food, 25 for other stuff. Then for outputs, we know there's 25 kilograms per week of the stuff was going to people as food, and so I think that's fair to say that just goes straight out. What remains is, that would be the remaining 25 kilograms we have to deal with, and part of that's going to solid waste, part of that's going to recycle, and we were also told that approximately 1 kilogram accumulates in the house per week. That might be kind of interesting here, because if you think about it, as college students, if you move dorms every semester or every couple semesters or whatever, you realize, over the semester you actually accumulate a lot of stuff. It's like, wait, how did all this stuff get here? Well, it only gets worse when you're in a house and then you live there for years, or more permanent. Stuff sort of accumulates sometimes, and if nothing else, you could say, oh, well, I bought a coffee table or something, or a TV stand, and that's 20 kilograms maybe, and that, if you just buy that in one semester, then that's 1 kilogram per week. If that's all the only accumulation that happens, something that kind of stays with you. So kind of funny to think about how that dynamic plays out in real life. So anyway, that means that we do have an accumulation term, but we're given exactly what it is. So when we set up our mass balance, we can say, okay, the accumulation is equal to what's coming in minus what's going out. There's nothing about reactions or anything, so it's just in minus out is equal to the accumulation. So when we then set it up, I'm guessing that the solution is going to look something like this. 1 kilogram is equal to these inputs, which is 50 kilograms. By the way, this is per week. Everything's on a weekly basis here. So something like 50 kilograms per week coming in. And then essentially it has to be, in order for this to be equal, there has to be a total of 49 kilograms going out per week. There are some unknowns here, so that's what we're going to be solving for, but those unknowns, whatever form they're in, should equal 49 because we have that 1 kilogram accumulating, staying in the house, adding to what's there, right? So it's going to take some form of this, but be branched out into a little more complex. And that's probably too small, so let me fix that. I'm just going to break this into 2 pieces. It'll just take me a moment. Okay. All right. So hopefully that's a little more legible there. All right. So when they go to solve the problem, then we had that house, and we labeled the inputs and outputs. We've got food to people. We've got solid waste to the curb. And the incoming 50 kilograms of stuff. Okay, so it says write out the mass balance equation. That's going to say, and they wrote it like this: input equals accumulation plus output to people plus output to solid waste. If you do that mental math, you'll see that's the same thing as starting with accumulation on the one side and saying that's equal to inputs minus outputs. They just flipped it already, right? So we could start with accumulation equals in minus out. And of course, these are rates, right? Input rate. And then, so what they did was they said, okay, well, the input is just going to be, we're going to take that on the left side and say input is going to then be, you add output to each side. That means that's just going to be the accumulation plus output. Okay, so that's just all they did there to get that first step. And again, this is just very basically from the fundamental assumption that mass is not going to be created or destroyed. It's just where we're going from. So then now we need to calculate the known inputs and outputs. So the inputs we know is 50 kilograms per week. The accumulation was given 1 kilogram per week. So the outputs, here's where we come to the question, and here's where we start thinking to ourselves, okay, what am I solving for? And perhaps maybe we should have been thinking of that before, and then we would have thought to ourselves, okay, we're going to find the unknown in the output somewhere, because the question is asking how much solid waste is being put to the curb, so that's one of the output terms. That'll help you design the problem in your mind to say, okay, what am I looking for, and where all does that appear in the problem? Is it a flow rate appearing in a couple places? Is it a volume term? What is it that I'm solving for? And here, it's going to be part of the total output. So the output to people is simple. That was already given. That's 25 kilograms per week. So that's here with the 25 kilograms to the people per week. And then the remainder is output to solid. Okay, so I'm happy to see that I'm tracking with them because I was not reading while talking. I'm not good at that. Yeah.
So 25 kilograms of food to people be a pay rate?
What was that?
Would it be a constant pay rate?
Well, they're constantly consuming it. I mean, they're generating it in terms of their buying groceries and bringing it to the house. Okay. And then the output then is like, if you think about the way food would leave the house, it's like you take it from the refrigerator and let's say go on a picnic. Okay, then it's in the human body, and then it's either going to CO2 or going down the drain, which they didn't show the drain in this schematic here. But I guess you could, but we're keeping it simple, right? We're just assuming that's gone to people and no longer going to be like a part of the household stuff. So that 25 kilograms per week for food is just sort of gone that way. All right, so then that leaves us, and actually this diagram right here is kind of nice. It shows, we get plus 1 kilogram every week inside the house, 50 coming in, 25 going out as food. That means we have to have 24 going out here as solid waste. And again, that's that 50 equals 1 plus 49, right? So we can say the solid waste here is 24 kilograms, but I think it also said there's some recycled, if I'm not mistaken. What's that?
About 1/4.
Yeah, so 1/4. So it should be 1/4 of that 24, and that should be 6 kilograms. Okay, so this is the next part. Mass balance equation. Okay, because the recycled amount is, 1/4 of the solid waste. The output to recycle then is 6 kilograms, because that 1/4 of 24 is 6, right? So we had the 50 coming in. We had 25 going out to people. We had 24. We had 1 accumulating, and then this 24 goes into 2 parts. So then we have 24 times, we could write it as 0.25, so 0.25% is being recycled. And then we have whatever is not recycled, we could write as 24 times 0.75, and that's what's going to the curb. Of course, you could also just say 24 minus 6 is 18, right? So that would be 18, and this is 6. Okay. And in that way, you can get the answer. And you can also see we solved for a few different things here. If we were interested in knowing what was the amount recycled instead of the amount to the curb, we would have had that one step before. So hopefully, this is a simple example of using one of our mass balance equations, this y equals mx plus b sort of things. Remember, we draft up that general equation based on the principle of this accumulation is inputs, outputs, right? Later we'll add reactions to that as well. But it's very straightforward in terms of the components that add to it, and then it's a matter of just doing some algebra to find what you need out of it. Maybe you solve for x, maybe you solve for m, maybe you solve for the recycle and not the solid waste here. Okay, any questions or issues with that? Okay, makes sense. Seems like something that maybe you could do without any environmental engineering knowledge at all, but this is sort of paving the way to approach these types of problems, this mass balance approach. It turns out to be very helpful and very powerful. Okay. A few other things that I want to talk about before we really dive into reactions and reactors and kind of the other physical processes is some unit conversions. I don't want to belittle your knowledge, intelligence, any of that. So I apologize if this is kind of on the simple end, but I did want to give it a nice covering to make sure that we're all on the same page, we're all comfortable, and this is not going to be an issue. Okay, so part of this class, we just want to get you up to speed with some things, and some of it will probably be new to you. But the very basics of unit conversions you've done for years, right? So I'm sorry, I don't mean to insult anybody's intelligence here, but I'm just going to go through it kind of quickly. First of all, noting that, so here's a table from one of the books that I'm using, not the one I assigned, but the one I assigned to have unit conversion tables, whole appendix with stuff like that. So be familiar with the process of going to look up a unit conversion. Maybe that's, maybe you do that on your phone, maybe you do that on the computer, maybe you do that in the back of the textbook, right? There's going to be resources. In terms of the SI units versus US or US customary system, I think most people would agree SI units tend to be simpler and easier because metric systems are just handy. Base 10 is quite nice to convert things. But that's not the world we live in, so sometimes we're going to have to convert. So I guess a basic principle here is just to harp again on tracking your units, right? And what I mean by that is if we're doing some conversion, talking about units, it seems obvious that I would say, track your units. But when we want to know how many meters is 1 foot or something like that, well, be extra explicit about it when you're doing unit conversions. So write everything out more elaborately than I just did. Okay, make a habit of saying, okay, well, I mean, starting here, maybe that's fine. But once you go and take a look at your conversion, if you write your conversions as fractions and be clear with your units on each side of the component of the fraction, it's going to really help you and simplify things. And it's just something that, you've done before, but it's something you still can mess up on, right? So this here says, for quantity of length, SI units is meters, SI symbol M, and then these 1 foot. And the conversion factor here, if you read the table's ledger here, it says SI symbol times conversion factor equals the SI units. So that's a piece of information in the table itself, not in that unit conversion. So what we can do with that is say, all right, this meter, so we'll say 1 meter times the conversion factor. This is 3.2808 equals the US unit. However, what I'm going to do here is I'm going to include here, this is feet per meter. This is what I mean when I talk about be very explicit. And in fact, you could do one better and say this is 3.2808 feet per 1 meter. Okay, you can go that far to just really make it clear to yourself exactly what's going to cancel. The 1 meter here, the 1 meter here will cancel, right? So do yourself a favor, even on simple, stupid things, start practicing so that you, so that you can do these properly. So that would give you 3.2808 feet, right? So that's how that conversion will work. So then we can see, oh, well, I wanted to know how many meters in 1 foot, so let me do that in reverse. So we'll just do that real quick. So this is 3.2808 feet. So that's one way. So that didn't answer our question. Instead, we've got to do it in reverse. So we can say, okay, well, we have 1 foot, and we want to get this in some amount of meters. So we can take this and say, okay, well, how do I manipulate this fraction so that I convert to meters from feet? Then it becomes very clear that all you need to do, use the pen correctly, is multiply this by the 1 meter divided by 3.2808. Right? You just invert it like that. That's no problem. So you could say divide. I like personally to just multiply everything and invert it as needed. So that would be 1 meter divided by 3.2808 feet. And you'll notice then that the feet cancel. You can confirm to yourself that you've done it correctly because your units are canceling properly, and you're left with just the meter. And then that is whatever 1 divided by 3.2 is. It's probably going to be something around 0.3 something, right? And if somebody wants to do that for me, go for it. Or I'll just do that. Okay. So you get the point. You've done this before. Really not intending to insult your intelligence by going over it, but I do want to stress, be careful with it, be methodical with it. It's going to help you. Okay. A lot of people will do the little conversion charts or something like that, where you just put these components in each of those cells and line them up that way. I see a lot of people do that. It's no problem. It's the same thing, right? Whatever your method of choice, be methodical, track your units. It's going to be helpful. It's especially going to be helpful once we start dealing with units that are a little, perhaps, less familiar. So liquids you're probably fairly familiar with. We'll talk about gases as well here in a moment, and probably get into a little bit further with gases. And just as we build into the class, there'll be new concepts, new units to work with, and that's just going to happen. So make sure to have that habit in place. If you are getting confused on something like that, don't feel ashamed. It happens sometimes. You just sort through it. Get some help. Ask a friend, like, hey, what am I missing here? I feel like I'm missing something. Like, help me out. Ask me. Feel free to get help, and don't let something like that prevent you from going on and learning the concepts and the actual skills here, because this is something that we all know you can do. Okay, so a few common practices for units, manipulations, measurements, analysis in liquids. You can have stuff per volume. That would be like mass per volume or number of bacteria per volume, something like that. Sometimes you could also do mass per volume with a liquid, right? Maybe I'm adding 5 grams of sodium chloride per kilogram of water. And if you're talking about seawater, that's not nearly seawater strength. That would, if you do, that would probably be like brackish water. If you do 25 grams per kilogram, it's like 25 grams of salt in my bottle of water here, that gets you to more like seawater strength. If I've done that right. So anyway, we do sometimes moles per liter. We'll go a little more in depth into chemistry in our second segment of the class. But essentially, moles, it's a number. It's like dozen, how many dozens per liter. And we designate moles per liter with a capital M. That will be important as we go. So that the stuff per volume metric can be number or mass. And sometimes we'll do it mass per mass. Now, if we're doing mass per mass, a lot of times what we'll do is express it as a parts per million, parts per thousand, parts per trillion, something like that. And just as an example, so parts per trillion is kind of funny because it could also be parts per thousand. And literally there's not really a difference. It's PPT either way. Sometimes I think people would give a capital T for thousand. Seawater, when you measure it this way, this is the mental gymnastics I was doing a moment ago. I was double checking myself. Seawater is approximately 25 to 30 range of salt parts per thousand. So we'll double check myself here. A couple of common relationships, assuming we're dealing with water, which has a density of 1 kilogram per liter, like we talked about last time. If we're using that, then 1 milligram per liter on a weight basis, on a parts per mass basis, you could have 1 gram per cubic meter, and that's the same as 1 milligram per liter or 1 ppm. So then 1 gram per liter would be 1 parts per thousand. So when I said 25 grams in my bottle, I think I was correct there. That would be the appropriate thing to get close to seawater strength. You could go the opposite way and say 1 microgram. So the mu here is micro. Make sure you know that. So microgram per liter is 1 milligram per cubic meter. That's the same as saying 1 part per billion. And this is by mass or by weight. There's one caveat here. If you're adding so much salt or so much solute of some sort where you're changing the density of the water itself, maybe it's a lot heavier now, something like that, then you'd have to adjust for it. You could do that very easily by multiplying by the specific gravity, because essentially what you have here is mass per volume, and you're saying that's going to be equal to a mass per mass, but that whole mass per mass assumption really was using the assumption that you had a 1-to-1 mass per volume conversion with the whole kilogram per liter thing. When you have 1 kilogram per liter, this becomes really simple, because how can you equate mass per volume? Well, it's because you have 1 liter per 1 kilogram. And so if you do it that way, you can cancel that and be left with mass and mass. So really the specific gravity thing was here the whole time. We didn't show it because 1 liter is 1 kilogram. Okay, so that's just an elaboration there, and a lot of times it's just convenient we can use parts per million. So you'll see that in a lot of problems. You'll see, okay, we have 5 ppm of chloride in the water, or chlorine, or whatever it is that we're adding or using, and it's just going to talk about it in that sense. What that means is that's 5 milligrams per liter. Okay, does that make sense? Okay, and some of these you might have to encounter in a problem before it kind of clicks and be like, oh yeah, I needed to do it that way. So it might be useful to go ahead and remember that 1 milligram per liter is the same as 1 parts per million. Of course, you can calculate it with the density of water. It's not that, that's not going to be hard. But what you should recognize is, in liquids at least, when we take ppm, that is usually what we're doing, is taking 1 part mass of the solute, the salt, whatever we're dealing with, per mass of water, or liquid. Okay, so we'll take a little example here. Not really getting into too much chemistry yet. I will remind you, this is very, very basic chemistry, so all I'm going to say is, when you're looking at the periodic table, you got the atomic mass units here, and that's how many grams per mole there are for this element. So this is fluorine, and so fluorine is essentially 19 grams per mole. You should remember that, and we'll review a little bit more when we get to the chemistry section, but that's pretty much what you need for this problem. And I would assume you know it, but here it is for you, regardless. So, fluoride concentration in drinking water may be increased to help prevent tooth decay by adding sodium fluoride. And I need to add sodium here too. I'll find that for you. Because this is NaF that's going to be added. So I'll get the sodium there in a moment, which I think is 22, 23. Okay, so, however, if too much fluoride is added, it can cause discoloring, mottling of the teeth. The optimum dose of fluoride in drinking water is about 0.053 millimolar per liter. If sodium fluoride NaF is purchased in 25 kilogram bags, how many gallons of drinking water would a bag treat? And assume there's no fluoride already in the water. So take a couple minutes and work on this problem. We'll do more of this with the chemistry, but for now, just treat it as a unit conversion problem, looking to convert between the grams per mole pieces here. So it'll be a little bit of a preview for chemistry section. Yeah, we'll take sodium as 23 grams per mole. And just as a reminder, with NaF as the salt, we're just adding those two atomic weights, and we'll get a molecular weight of 19 plus 23.
So when it says fluoride, it means sodium fluoride, right?
When it says, okay, so that is a good question. Here, we've got 42 grams per mole for the sodium fluoride, NaF. When it's talking about this here, that's talking about F minus, because what's going to happen is NaF is going to be added to the water, and then it will be Na plus and F minus. But it doesn't really matter too much because, again, this is simple enough where it's 1 mole of this goes to 1 mole of this and 1 mole of this. So you can, if you know the moles of NaF, then you know the moles of F. Okay. And you also know the moles of Na. Okay. I'll show you, like, in case there is any confusion here, I'm going to write it out nice and explicitly with units. If you are getting stuck, write out the units, right? And use this relationship from this equation that I just wrote you. All right, so let's take a look together here. So first thing I would do is kind of identify really what we need to get the answer, and that is some relationship between the mass, like mass per gallons, and then we can get that. We know the mass that we have. That'll give us the, then we can find how many gallons we can treat with that mass, to get our answer. So in light of that, what I thought was, okay, well, let's start by saying, okay, we have this concentration in 0.053 millimoles, and I want to know how many grams is that. So that's millimoles per liter. If we write that out differently, we could say that. Millimoles F minus per liter, because F minus is what we're treating with. And so we want to know how many grams per liter that is. And then we can convert from grams to kilograms, we can convert from liters to gallons, and then we're going to have that relationship, and it's going to be easy from there to solve. Now, you could go a couple different routes here, so you don't have to do this. But I want to start there. And actually, I've already set something up a little bit incorrectly, because I don't have grams of fluorine in my bag, fluoride. I have grams of NaF, sodium fluoride. So I've already made a small mistake here that I just caught with my unit. So I have moles of F minus, and I'm trying to get grams, but I'm actually trying to get grams of NaF. So when I convert to this grams of fluoride here, if I were to continue this, I would get grams of fluoride per liter. That's not what I need. So I need to back up a step, and instead of using the 19 grams of fluoride, I need to add a conversion at least. And I'll do the molar conversion first. So I'm going to back up just a little bit here and say, okay, I've got the moles per liter of fluoride, F minus. But now I need to make sure that I get it in terms of moles of NaF. From our little chemical reaction I gave you here, we can say that there is 1 mole NaF per 1 mole F minus. So that is a easy way to convert the molar things to NaF. That gets us what we want. And that makes sense. For every 1 molecule of NaF we dissolve, we get one atom of F minus. Right? That's the chemistry. We'll review that some more later. But that gives us that conversion. If that cancels these, now we have moles of NaF. And by the way, I'm sorry, I should have been a little more explicit here. That 0.053 millimoles per liter, I converted that to, I divided it by 1,000 to get moles, because there's 1,000 millimoles in 1 mole. So if I want to go from millimoles to moles, I have to divide by 1,000. So I went from 0.053 to 0.000053 and expressed it as times 10 to the minus 5. 5.3 times 10 to the minus 5. So that I just converted there from millimoles to moles. Now I've got it in 5.3 times 10 to the minus 5th moles NaF per liter. Now I can multiply that by the 42 grams per mole, 42 grams of NaF per mole NaF. And that'll give me a value for my mass there. I have not done that one yet, so we'll just grab Excel. How many of you guys like Excel? Only a few? How many of you guys have a graphing calculator? You learned to use them pretty well over the years? No? Some yes, some no? It's interesting to me because I'm obviously a little bit older than you guys, but not quite the generation of some of the other faculty maybe teaching you. So I grew up using Excel and graphing calculators in school and all that. And so in school, we we would use graphing calculators a lot, but now I realize, well, you could probably have a graphing calculator function, an app on your phone, right? Did anybody have that? Does that exist? You know, some, yeah, okay. So it's kind of funny how the world changes, but I'm just kind of a little bit curious. One of the things I want to do with you this semester is kind of give you some practice and a little bit of training in that regard. Okay, so I'm just going to do this in Excel real quick. So I'm doing that multiplication, 5.3 times 10 to the minus fifth times 42. That's going to give us 0.0022, and that's going to be grams of NaF per liter. Oh, that was 00 or 0? 0. Per liter. Okay. So with that, then we have something close to this mass per gallon, but really what we want is kilograms per gallon. That's going to be the easiest. That's kind of what I'm aiming for. So we'll take the 0.0022 grams NaF per liter. We can multiply that by 1 kilogram per 1,000 grams. We want to be very explicit with it here. That gives us, we can write that as 2.2 times 10 to the minus fifth kilograms for every liter. And from there we can say, well, we want to go from liters to gallons. And so we will take that and say, let's see, we can just actually multiply it directly. So multiply this by what I gave you here, and I'm sorry, I should have made it probably bigger, is 3.785 liters in every gallon. That's going to cancel these liters. We'll be left with gallons on the bottom. So that's what we want. So we'll take this. I'm going to say this number, we needed to divide by 1,000, which we did. And then we'll take that number and multiply it by 3.785. So that gives us 8.43 times 10 to the minus 6. That is kilograms of NaF per gallon of water that we treat. Okay, now certainly you could have solved for this a little bit in a different way, because I still have one more step to do here, and that's to take the gallons to the other side and like actually solve for gallons. So if I get 8.43 times 10 to the minus 6 kilograms, if I needed that many kilograms in every gallon, I can invert that and say, okay, well, that's how many gallons I can treat with 1 kilogram, except I'm going to use 25 kilograms, right, for the problem. So with all that, let's see. I'm going to erase a little bit here to make a little space. Hope that's okay. Okay, so we have 25 kilograms of the stuff, and we want to know how many gallons can we treat. Well, if we take this and divide it by our number down here, those units should end up the kilograms will cancel, and that'll give us our gallons. So this is just one more unit conversion here. Or I could write it as multiplied by, it takes 1 kilogram, or it takes 1 gallon, excuse me. In 1 gallon, you need 8.43 times 10 to the minus 6 kilograms. So then the kilograms will cancel. That'll get us our final answer. And we can say this would be 25 divided by that number. And it says we can treat quite a few gallons of water. And I think the book, if we were to look at the solution, it says you can treat like population of 20,000 people for X number of days or years or whatever. So that's quite a lot. So, and if I look at putting this in scientific notation and rounding it, we can just say that's 3 million. So 3 million gallons approximately. Okay. A little messy, and I apologize for that, but does that make sense? You okay about that? All right, so just a bunch of unit conversions, and you saw me make a mistake. Can happen sometimes, but that's why I'm saying, like, be explicit, be careful with the notation. So, I have a little bit of pressure to talk, write, and read and comprehend all at the same time up here. You might not think it, but it's a little stressful sometimes. And, double check myself. Am I doing something stupid? Am I writing the wrong thing? So please always check me here. But what you see is having that system in place, it became apparent to me pretty early that, oh, wait, this is the wrong unit happening. So you'll have stress on your exams. Maybe you're cramming to get a lot of homework done in time. There will be stress sometimes, so do that to reduce your stress and get right answers more often. Okay, so moving on to gases, something maybe you've talked less about, and I'm also going to bring in the ideal gas law here. So for gases, we can think of this room, for example. How many coronavirus particles are in this room? And let's say the room is, 40 cubic meters or something. That would be an important question, and hopefully it's pretty much zero, right? But if you wanted to calculate exactly how much airflow that filter needs to handle, you would have to start thinking about, okay, what mass, or how many, I guess, in coronavirus case, particles are there per volume, and so how do we deal with volumes with gases? Volumes with liquids are kind of simple because at least water is pretty much incompressible. Fair number of liquids are incompressible, meaning you can pressurize it, but it doesn't change its volume. Air is a lot different. You can pressurize air, and it's going to change the volume, right? So you just think of a scuba tank. You've got a lot of air in a small space. It's a big volume. It's a small volume, but a large mass of air. And when depressurized, that becomes a big volume of air. So for gases, most of the time we're dealing with volumetric. Now, I mentioned the coronavirus. You might have a number of viruses. Other things, maybe you'll have a mass of a pollutant. But sometimes we'll just have a gas. Like how much of the air we breathe is nitrogen versus oxygen, for example. And there we would often use volumetric units. So volume per volume. You could think of it, if it's a gaseous pollutant, something that's in the gas phase rather than like a solid particle, then a lot of times we'll measure it like what volume of gas, of a gas pollutant, per million volumes of air. And the per million thing here is just, that's a common amount, right? It's common that we have 1 part per million. The air we breathe, if we were to talk about CO2, which is not directly a pollutant in terms of like a toxin or anything, but CO2, for example, is around 400 parts per million. So again, thinking back on from that recorded lecture, parts per million, parts per thousand, parts per 100 are all kind of similar, and parts per 100 is recognizable as percent. Cent meaning 100, parts per 100, right? So percent right? So if that's the case, then it's just 1 part in a larger volume, okay? And it turns out that a lot of air pollution is on the parts per million or parts per billion level. You could go down further, parts per trillion, things like that. The other way you can do that, instead of describing it by like more and more volumes of air, we could just keep that 10 to the 6 kind of standard perhaps, and then change the prefix, right? So microgram versus milligram versus maybe you could go nanogram per cubic meter. And it turns out that 1 cubic meter is, a pretty reasonable conception that we could have, and perhaps a pretty reasonable thing to measure that filter is cycling every minute or every 20 seconds or whatever. It's a tangible amount, right? We'd like to work with tangible stuff. So if we take that tangible one cubic meter and use a few references, then our parts per million is going to be that that milligram per cubic meter, or we've got parts per billion as microgram per liter. Okay. So I mentioned earlier there's the feature of gases that they're compressible. So this is where we introduce what we call the ideal gas law, and this is going to kind of change the situation in some cases, because we may need to know something more about the system than just the volume or just the amount of, like, the comparison, like how much CO2 or how much nitrogen versus total. So we have this equation PV equals nRT. That is the ideal gas law. And what this means is pressure times volume is related to the mass, or really the moles of stuff, of gas, times some constant times temperature. So it's relating pressure times volume. And that kind of makes sense, right? We take some volume and we compress it. That's you kind of know that's going to give us some form of how much gas there is, right? You take a scuba tank, it has some volume, but it's at a high pressure. That means there's more air in it. You've pushed more air into it. So pressure times volume is related to that number of moles. Write it like that. Times some constant times temperature. Now, there's actually a couple forms of this. You can do it in atmospheres for pressure. That's what we're going to do, and that's, I believe, the most common arrangement for our book. And really, I actually took a few different books, just kind of piecing what made sense to show you together here. And so, but it's very common to use pressure in atmospheres. The pressure of one atmosphere is literally at sea level. How much pressure does the air above you exert on you, above and around? That's what we call one atmosphere. So it's kind of a standard metric for pressure based on our atmosphere at sea level. Okay. And so we have some other references here just for your information, and this certainly you could look up. Will be in indexes, appendixes and stuff like that. Will be online. But one atmosphere is 101.325 kilopascals. So pascals, you probably heard another metric, and so kilopascals, 1,000 pascals, like kilogram. So one atmosphere is 100 of those, or 14.7 psi. So if you've ever filled a bike tire or a car tire, PSI is probably pretty familiar. Cars often run between 30 to 40 PSI for just normal commuter tires, somewhere in there. A bike tire, if you have like a racing bike, maybe you'll go all the way up to 120 PSI or something. That would be pretty extreme. So a standard bike tire, maybe 40, 50, just kind of whatever general purpose. So that gives you an idea. And you could say, oh, well, then a bike tire inflated to, 80 PSI, that's 4 atmospheres or whatever, 5 atmospheres, something. 100 kilopascals, that's what we call 1 bar, if you've seen that. And so that means that 100 pascals is 1 millibar. It's obvious if you do those conversions, but just a few things there to give you a little bit of a reference about what 1 atmosphere is. Hopefully that helps. So in atmospheres, if that's what we're doing with pressure, then the volume needs to be in cubic meters. This N is going to be in moles. And I don't think mass is really the right term. I think it kind of works, but just the book should have called it moles, but I just copied it like the book said. R is this ideal gas constant. And if you were to use a different pressure unit, then R would be different. So if you're going to use pascals instead of atmospheres, this value would change because, well, it kind of has to, and you'd have a different value there. So double check that. If you are using a lookup table, make sure you've got the right units in place to match your system, right? So, and one thing you'll notice here is we've got liters. So in terms of the volume in cubic meters and the volume in liters, I think we might need to convert. Let's see. I'm gonna have to check on that because I just took this straight from the book and I'm questioning now how that works out. It may just be included in the actual constant there. So I'll take a look at that. But anyway, the point being, it also depends on temperature. That's in Kelvin. So if you take Celsius and add 273.15, that gets you to Kelvin. So all of this is just ways to, unit conversions that might be necessary in order to relate gases in terms of their volume, their pressure, and the temperature, and the number of moles we have. With that, there's actually some convenient things we can do. It turns out that all gases, all ideal gases, I guess there's some strange ones out there, but most gases behave fairly much like ideal gases, and if you compress one gas versus the other, it turns out it doesn't really matter what they're made of, as long as they're an ideal gas, which most are. So you could have a really, you could have a gas made up of atoms that are really heavy, and it would actually act the same way as a gas made up of atoms that are really light, for example. So helium is going to behave the same way as air, but it's just going to be less massive per volume. Okay, so that's important. That's why balloons can float. If this behavior depended on what's making up that gas, it might be a different story. Okay, so we've got an example here, but only a couple minutes left in class. So maybe we'll pick up here next time and go a little further with the ideal gas law. Any questions or concerns before we end? Okay, so next week I'll start doing attendance sort of stuff a little more routinely, rhythmically. But for now, that's all for today.